Hello everybody. We are going to now take a look at the bulk distribution coefficient. So in a previous video lecture, we looked at these things, the partition coefficients, or KD, and we kind of glossed over the bulk distribution coefficient. But these are very important for us for doing calculations of how elements are distributed between different phases. So you might recall from the previous lecture that this bulk distribution coefficient is a weighted partition coefficient, where we take the sum of all the partition coefficients for the phases that are present and we weight them against the amounts. Well, we're going to go back to the examples that we gave in the prior lecture of olivine and plagioclase and nickel and calcium. So the first thing we're going to look at is this value xj here. So xj is the amount of any individual phase. So in this case, I've drawn 12 crystals of olivine and 7 crystals of plagioclase. They're not exactly the same size, but let's say they are, because this is really a volumetric proportion. So if they're taking up the same amount of space, those individual crystals, then we can write the fraction of olivine. This xj now becomes xol, ol for olivine. That would be the total number of crystals of olivine, which would be 12, over the total of all of the crystals. There are 19 crystals altogether. So the fraction of olivine, for the purposes of this distribution coefficient, would be 12 over 19, or 0.632, or we can write it as a percent, as 63.2%, but we'll use it as a fraction later on. And we could do the same thing for crystals of plagioclase. We can write a x sub PL, PL for plagioclase. We have 7 crystals of plagioclase out of the total of 19 crystals altogether, and that's 36.8%, or as a fraction, 0.368. So those are our xj that are going to go into this equation. So now let's take a look at the example of nickel. In the previous lecture, we talked about nickel being compatible in olivine and incompatible in plagioclase. Well, if we have nickel that is being absorbed by olivine, but it's being rejected by plagioclase, what is the net effect when we have these two minerals crystallizing together? And that's what the bulk distribution coefficient is going to do. So again, here's that complicated looking equation we looked at earlier, but now we can break it out into its various parts. This summation just says ahead of time we don't know how many phases we might have in a system. But in our particular case, we do know. We have 2 phases, olivine and plag. So we can drop the summation sign and then just talk about the xj for olivine, the amount of olivine that we have, and then the kd for olivine, and then the xj for j, now plagioclase standing in for the j, the amount of plagioclase that we have multiplied by the partition coefficient. To put some numbers on this, the D for nickel, the bulk distribution coefficient, would be the amount of olivine, which we found earlier was 63.2%, multiplied by its partition coefficient, which is 10, plus the product of the amount of plagioclase, which is 36.8%, multiplied by its partition coefficient, which is 0.01. And when we do that calculation, we find out that the bulk distribution coefficient for nickel is 6.32. So that means nickel is generally compatible in all of the solid phases. Even though it's incompatible in plagioclase, it's strongly enough compatible in olivine, and there's enough olivine to absorb it, that this bulk distribution coefficient is still greater than 1. So as these crystals form, there will be more nickel going into the total solids, mostly into olivine, not much into plagioclase, but there will be more nickel going into the solid phases than will be left behind in the liquid. The liquid will be depleted in nickel as the system crystallizes. Let's take a look at calcium. So in our previous example, we found out that calcium is incompatible in olivine, but compatible in plagioclase. For this very same system here, we can do the same kind of calculation. I'm not going to write the general equation here, so we'll just look at the particular case. the bulk distribution for calcium would be the amount of olivine, 63.2%, multiplied by its partition coefficient, 0.2, plus the amount of plagioclase, 36.8%, multiplied by its partition coefficient, which is 12. And we'll get a bulk distribution coefficient of calcium of 4.55, a little bit less than we found for nickel. Again, however, even though olivine does not absorb very much calcium, the bulk solids, olivine plus plagioclase, will still absorb more calcium in total than the liquid will. So as the system crystallizes, calcium will be depleted in the residual liquid, with most of the calcium going into solid phases. Of those solid phases, the olivine will absorb almost none of the nickel. Most of it will go into the plagioclase feldspar. And when we have another lecture, we'll look at how we can do these calculations to model the evolution of a liquid depending on the values of these bulk distribution coefficients D.